Hi guys, and I'm back today with the second part of the time series lecture. Today we are going to talk about something which is extremely interesting part of time series, which is time series prediction, right? So as I had mentioned in the last lecture, so time series work mostly is divided into two categories. One is time series analysis, which is basically breaking down the time series into its corresponding components. You know, the trend line, if you remember, trend, monthly analysis, yearly analysis, and basically figuring out what is a monthly pattern which is repeating, which is the yearly pattern which is repeating, which is a weekly pattern that is repeating, and then the overall trend line, right? And we remember that our time series was composed of all of these patterns, right? So that was time series analysis. So time series prediction is the next part of it, and is basically kind of takes on from there, which is predicting the future time series, right? Now that you have the entire time series history, how can you use that to kind of predict time series in future? So that is the part that we are going to talk about today. But one thing that we kind of need to be very clear about right now is that time series analysis as such is something that is something that was new probably per se, but time series prediction is something that is going to be exactly same as what your normal machine learning prediction is, right? So in normal machine learning prediction, you have used all kind of techniques, right? The classification techniques, regression techniques, the imbalance problems, everything that you have dealt with, they're the same thing that you're going to deal with right away here as well, right? So frankly, time series prediction is not very different from your normal predictions, the machine learning predictions. There are slight few things that we are going to talk about, slight nuances about how you do trend test split, what is the exact kind of feature that you try and predict. And obviously a very important part of time series prediction is doing feature engineering. So we are going to spend a lot of time understanding what are the kind of feature engineering that you can do for time series data. But that's about it, right? So we're going to spend a lot of time understanding what are the different kind of feature engineering that you can do, which are very specific to time series kind of data. But apart from that kind of feature engineering and small nuances here and there, frankly, the rest of it is exactly going to be the same, right? The way you had used housing price prediction, right? You are trying to predict house prices at for each of the given the different house feature levels. This is the same kind of thing we are going to do. So we are going to say predict the stock prices given different features about the stock. The only thing is, in this case, we can also have use the past values of the target variable, right? In case of your housing price prediction, you cannot use the prices of other houses to predict the house price, right? But in case of time series, you can basically use the target variable, the older values of the target variable, to also predict the current target variable. That's mostly the major difference, major understanding of what is different from normal time series prediction and normal machine learning prediction, right? So that's about it. So it's mostly about the feature engineering part that we are going to go and deal in a much depth. But apart from that, rest of it is pretty similar to what you have done. In fact, almost absolutely similar. So let's get started with it, and we kind of, as we go into delve into the details of the section, I'm gonna kind of caution you into parts where we are kind of deviating from the normal prediction methods, but mostly it's the same prediction method. It's just that we are gonna just learn about some more feature engineering tricks and all of that we are gonna do for this kind of thing. So as I start, so the first up is talking about model driven predictions. So that is fairly nothing but, say you're trying to predict the electricity demand of a country or a state, right? At any particular point in time. And as you can see, the electric demand is basically as a function of current temperature, it's a function of the strength of the population, it's a function of the population, strength of economy, and all of those different features, right? Now, as I had already said, this is exactly what you have done in supervised learning, right? In case of supervised learning, this ED, right? ED is basically the electricity demand, is basically the target variable or the dependent variable. And what is it dependent on? It is dependent on the independent features, right? So current temperature, strength of economy, population, time of day, day of week, all of these are your independent features, right? So that's your dependent variable, that's your independent variable. And this is the entire paradigm of supervised learning, right? So there's nothing absolutely new that we are doing out here. That's the basic thing that I've been saying now. So let's kind of go ahead and see what is there ahead. So as I've already said, that you kind of the same methods that you have used in classification, regression, the same techniques, right? Everything that you have discussed, though all those things are going to stay the same, right? So we are just going to learn about some new kind of techniques about feature engineering. So now first is assumption, right? So before we kind of go there and talk about assumption, let's first kind of look at time series again, right? So this is your time series Y. And as I mentioned in the earlier lecture also, so time series is nothing but this one particular quantity y that you are measuring over a period of time, right? So this is t equals to 0, this is t equals to 1, this is t equals to 2, and so on and so forth, right? So this is basically what is a time series data. So now in time series data, so say if you have to kind of try and predict this, right? So this is a continuous variable, right? So this is kind of continuous variable, and y is basically nothing but a function of t, right? This is what we already know, that's what it is, right? So this is a function. So in this kind of case, you can see this is probably a linear function of sorts. So y kind of varies linearly with time. So you can use your linear regression, right? So you basically say y hat is equals to m t plus c, right? So this is your dependent variable, which is your dependent variable, and this is your, sorry, this is an independent, my bad, this is independent, and this is dependent variable, right, or the target variable. So as you can see, this is something that you're very familiar with. This is the equation of a line. You can basically try and predict this particular curve using a line, right? That's linear regression. That's something you're familiar with. So in case of linear regression, we know that your actual value, y actual, is nothing but y prediction plus some error, right? That's what is this. These are the basics of linear regressions. If you're trying to predict y using time, so as I have shown you, that's basically you can try and predict that using a straight line, right? If you're trying to predict y using time, basically using a linear regression like a straight line out here, then basically you would be able to do this, and then there would be some error associated with this, which is basically the concept of error and residuals. I'm not kind of going into there's a fundamental difference between error and residuals, but that we'll talk about a lot later in the course, but not right now. So basically whatever you call it, error, residuals for now, is something that we are going to stick to. And there are some assumptions that are there with when we did linear regression, there were some assumptions of our error, right? So the same assumptions kind of still hold in this case. So this is the first, these are the assumptions, right? So obviously they have to have mean 0. So this is how your error should look like, right? So if you have, this is your error and this is your time t, right? So basically your error should something look like something which is random like this, right? So this is your 0, this is the 0 line, right? So that basically means that your errors should be randomly distributed, right? And it should be basically not randomly, basically they should be random, they should not depend. So if your error looks like this, right, if your error is basically look like this, so that is violating a major underlying assumption of underlying assumption of linear regression, which is basically your error is basically related with your time, right? As your time increases, your error increases, right? So this is the heteroscedasticity assumption that we had in linear regression. So this is basically violating the assumption of heteroscedasticity. In this particular case, you can see that your errors are not basically varying with time t. They are completely randomly distributed around 0. And the idea is also they should be normally distributed with a mean of 0. So those are the basic assumptions that we have here. So basically that there should be a mean 0 and they should not be autocorrelated, which is basically, if you remember from last lecture, autocorrelated basically means that there should not be any relation between error, right? Ideally, if your error basically is a time series of itself, then basically there's a problem, right? Basically error also is related to your time t. That is basically the underlying assumption of heteroscedasticity. So every assumption that we had for linear regression, right, all of those assumption about the errors are still gonna hold in this particular case as well, right? So they are unrelated to predictor variable, which is basically in this case the time series, the value of t. So those, everything that had the error, the assumptions around error term in linear regression that we had are basically gonna hold true in this particular case also. So there's nothing more about it. So now we are going to talk about the feature engineering part, which is what I have been telling now for so long, that that is basically the most important part of your if you're doing time series prediction. The only thing to kind of learn new, right, from apart from what you already know, is basically this whole concept of feature engineering and how you can do that specific to time series data, right? So first up is the concept of trend. So the concept of trend is basically nothing but basically this particular equation, right? So if you remember your last day Australian drugstore data, right? And this basically looked something like this, right? So there was a seasonal pattern that was yearly pattern that got repeated. So this basically was equal to a trend. This was called trend. This is trend plus a seasonal pattern that got repeated across the years, right? So when you combine the trend plus seasonality, you basically got this time series data, right? So now if you can see this trend is basically something that is a straight line plot of y and t, right? So as I had already explained, you can basically try and predict this using y equals to theta naught plus theta 1 t, right? So this is a straight line. So this straight line basically is of the equation theta naught plus theta 1 t, right? So this theta naught and theta 1, right? This is theta 1, this is theta 1. This theta naught and theta 1 are basically the weights, and how do you kind of figure out the weights is using linear regression, right? Gradient descent, cost function, all of those concepts, right? It's exactly same. So trend is basically the concept where you have y and you're trying to construct this straight line, which is nothing but y equals to theta naught plus theta 1 t, and that's all about it, right? So for this, so if your currently your time series data looks like this, right? So your time series data is this, where you have say different y values, and then you would have multiple values like this, right? So then to do if you kind of want to get the trend data, so then for that what you have to do, so this is December 14, right? And then this is Jan 15, and then this is Feb 15, then March 15, right? So this is how your data looks like as of now. So there's no T out here, so this is how the data looks like. So there is just 2 rows, 2 columns, and for each row you basically have different months of the data and your corresponding sales value or say stock value, whatever you want to talk about. So basically those are your Y values, right? So for feature engineering, if you want to kind of construct this trend data, so all you need to do is, because this, as you can see, y is dependent on t, right? So t is the independent feature that you need to create. So t is basically nothing but the values, right? So this is 0, this is 1, 2 and so forth. So all you need to do is basically create this extra feature, which is 0, 1, 2, 3, 4 and so on and so forth. If you construct this and you use these two features, you can basically construct the trend line, right? So you basically would your linear regression would basically have x as the t variable and your y as the current y. If you use that, you would basically get this particular trend line, right? So that is the same concept as linear regression, so there's nothing much about it, right? So all you need to do for trend analysis is basically add this feature, right? T equals to 0, 1, 2, 3, right, for each of the rows. That's all about it, right? So now let's talk about the next kind of feature engineering, which is basically, now that you know the now you know the trend analysis, now you also need to capture the seasonality, right? If you remember this graph, so your current data is, you have been able to capture trend, but you also need to capture seasonality, right? So to capture seasonality, all you need to do is basically construct seasonal features, right? So these are all feature engineering, right? To construct trend, you did a feature engineering where you added t equals to 0, 1, 2, 3 for each of the rows. And now for seasonality, you have to again add some column which basically captures a seasonal trend. That's about it. So in this kind of case, you can basically have multiple frequencies, right? Seasonality can be captured in weekly terms, in terms of monthly trend, in terms of quarterly and yearly trend, and in terms of hourly trend, and all those sorts of things, right? So basically you can capture the seasonality in all of them. You can use probably some of them. Obviously it goes without saying that to capture something like this, you would basically need to have a lot of domain knowledge to kind of understand. So if it's stock data, is it varying across a weekly pattern? Is there a seasonal, like a monthly pattern, or is there a quarterly pattern? Is it a yearly pattern? That's something that would come with domain experience a lot, so you probably would not know. If you do not know which is the kind of granularity of seasonality to look at, obviously the idea is you use all of them and see which is the one that is performing, which is having the highest feature importance, right? So that's a common idea. So here are some examples, right? If you're trying to say you're looking at weekly kind of an example, which is basically electricity demand, right? So that probably spikes during weekdays, spikes during weekends compared to weekdays, right? So there's a weekly parameter to it. And also there's a seasonal, say monthly seasonal parameter to it, right? So for example, there would be electricity demand would be a lot higher, say for example, during summer months than as compared to winter months. So those are things that if you have some domain knowledge, you already would know. If you say do not have a domain knowledge, say for a stock data, you really do not know if there's a weekly pattern or if there's a seasonal pattern or there's a yearly pattern. As I said, the idea is to take all of them, right? So now the question is, how do you kind of do that? How do you kind of capture? What is the feature engineering that you need to do? So the feature engineering is simple, right? So basically all you need to do is say you are trying to capture the quarterly trend, right? So if you know that there's a quarterly trend, so if probably each first quarter of the month there's a spike in the sales, and then the kind of sales kind of go down over the next 3 quarters. So for to capture that kind of a trend, you would basically need to have four. So we need to have, say, 3 features, right? So FQ1, FQ2 and FQ3. Not 4 but 3 features. I'm coming to that question of why not 4 features. But say all you need to do is basically say 1 if this is a quarter, 0. So in this particular case, this is December 14, right? So basically it's not quarter 1, it's not quarter 2, it's not quarter 3. In case it's a Jan, it's basically the first quarter, right? And then it's Feb, it's also the first quarter. And so you have April, right? In the case here, April 15, and April 15 is nothing but your second quarter, right? So this is 0 and this is 1 and this is 0, right? So to capture the kind of quarterly trends, you would basically have something like this, something like a feature engineering like this, which basically says that what is the basically which quarter currently this month belongs to, right? So if it's this month is belonging to the last quarter, so it's not 0, it's not 0, it's 0 here, 0 here and 0 here, right? It's not Q1, Q2 or not Q3. So obviously there's a question, why not add a FQ4 here, right? Why not actually have 4 quarters? Because actually in real life there are 4 quarters, right, in a year. So the idea is that you don't want to add an extra variable, which is the same concept of one-hot encoding, right? If there are n possible categories, you basically want to have a n-1 dimension one-hot encoding. It's because in case it's Q4, right? So Q4 is basically everything that is not, if it's 0, 0, 0 across Q1, Q2, Q3, that automatically implies that it's in Q1, Q4, right? The same concept. So that's why if you are kind of trying to encode into, say, weekly dates, right? So it's like Monday, Friday, Saturday, Sunday, and all of those 7 days as week, you would basically end up having 6 features, right? Because if it's none of the, say none of the 6 Monday to Saturdays, then it's obvious that the corresponding feature belongs to Sunday, right? Corresponding row. So this, for every row, you are basically trying to have this feature FQ1, Q2, Q3, which basically says that what is the corresponding quarter. In this case, because we are trying to capture quarterly trend, which quarter the corresponding month belongs to. Now that's one way. The other way to also capture quarterly trend is, for example, to say Q average, right? Where basically what you do is if for December 14 and for a quarter of the last quarter of 14, you basically calculate what is the Y average across the 3 months. For Jan 15 also, you basically capture the Y average of Q1 of 15, right? And then it's the same value for Y of Q1 of 15. All the 3 values are same. And then for April 15, you basically have Y bar of Q2 15, right? So for the first quarter, you're basically, what you're doing is for all the 3 months in the first quarter, you have basically computed another feature, which is basically nothing but the average across all these 3 months, right? So in this case, 3, 2, 1, these are the 3 values. So your average is 2. So this is value is 2 for each of the 3 months. So that's the concept of, so obviously as you can understand, instead of mean, you could do summation of 1, 2, 3. You could take mode of 1, 2, 3. You could basically take mean, median, mode, whatever you want, summation, weighted sum, whatever you want to do. So the options are obviously, as we have discussed, everything in data science is an open field. You can just decide what you want to do. And in a similar way, you can basically capture any kind of thing that you may want to do on a quarterly basis, right? So basically you would capture some value which is there for the entire quarter and use that across for the same values for the three months in that quarter, right? And you can capture weekly, you can capture yearly, monthly, bi-weekly, whatever you want to, whatever frequency level you want to capture, you should be able to do it, right? So the idea is pretty clear. So this is the second kind of feature engineering, which is basically, so this was for trend, right? And all of these 4 features, right? So all of this 4 that we have here are for capturing the seasonality, right? So now let's go back and try and understand what are the next kind of feature. So obviously I think caution part is, before we kind of go into the next part, Caution is basically, as I already explained to you, if you are having 4 quarters in a year, you always want to have 3 features into which you encode, right? Because obviously if it's 000 in the 3 feature, that obviously implies that it's 1 in the 4th feature. So you don't need to have an extra feature because of that. You can basically represent all your quarters just using 3 features as well.
Log on to GreyAtom's learning platform to unlock more free content. Subscribe to our channel and hit the bell icon for regular updates.